So we've got time for one more KF problem. I'm going to work an additional example of a problem that deals with complex ion formation. And we're going to take a look and see what concentration of metal ion is available after the complex forms again. So that we don't use the same ions as before and picking two totally different ions. And if we look at Hg2 plus, Hg2 plus forms a complex with iodide. 4 of them, 4 iodides per mercury 2 plus. So that would be Hgi4, 2 pluses and 4 minuses. Overall charge is 2 minus on the complex ion. So there's our complex that we're forming from Hg2 plus and 4 I minuses. The Kf for this complex out of our table, we'll look it up here real quick, 1.9 times 10 to the 30th. So what is the free concentration of Hg2 plus? In a solution prepared to be, we'll choose 0.40 molar Hg2 plus and 5.30 molar I minus. So our job is to kind of repeat our last problem with iodide in this case and mercury 2 plus. So we need our ice table once again. We show the formation of the complex. So it's Hg2 plus 4 I minuses in equilibrium with Hgi4 2 minus. So we set up our conditions, what we know about. So initially, a change, an intermediate, a change, and equilibrium. Because these are all ice tables because of the large K value that we're dealing with. So our initial conditions, for mercury it was 0.40 molar, for iodide it was 5.30 molar, and no complex yet. Okay, we need 4 times the amount of iodide as we have mercury, and we have more than that. So we're going to use up all of the mercury. So minus 0.40 molar, minus 4 times 0.40, that'd be 1.60 molar that we've used. And then the complex is 1-to-1 with mercury, so we gain 0.40 molar complex. So we reached intermediate. We let everything shift to the right. This is our intermediate stage. We have no mercury at the intermediate stage. So 5.3 minus 1.6 is 2.7. I think. Nope. 3.7. Molar iodide and 0.40 molar complex. Now we let it trickle back the other direction. We're going to measure how much trickles back. So we're going to lose 1x amount of mercury complex, gain 4x amount of iodide because of the 4 up top, and 1x amount of mercury because of the 1 in the equation. So we write our equilibrium conditions. X, 3.70 plus 4x, and 0.40 minus x. Those x's are going to be negligible compared to the molarities they're with because Kf is enormous. So now we have our concentrations in algebra form for our Kf. So we write our Kf expression. For this equation, we formed Hgi4 2 minus, that's our product, divided by Hg2 plus, and I minus, this time also to the 4th power. And that has a numeric value of 1.90 times 10 to the 30th. So we rearrange and solve for mercury. Mercury 2 plus moves to the numerator when we cross the equal sign, and the Kf value moves to the denominator. So the concentration of Hg2 plus, which is what we're looking for, is equal to the concentration of Hgi4 2 minus divided by I minus to the fourth divided by 1.90 times 10 to the 30th. So we plug in our numbers. And from our table, we have 0.4 up top. All over, I minus was 3.70. That gets raised to the fourth power, and 1.90 times 10 to the 30th. So once this thing reaches equilibrium, we're going to have free mercury, the value that we calculate here, 0.4 divided by 3.7, y to the x 4 to raise to the fourth power equals divided by 1.9 times 10 to the 30th. So 1.12 times 10 to the minus 33rd. That concentration right there is ridiculously small. It's not even a possible concentration. Okay, think about how many mercury ions there are in 1 mole, right? 10 to the 23rd, we have 10 to the minus 33rd molar. What that's saying is that we need 1,000 or more liters, probably even 1,000,000 liters before we can count on having at least 1 mercury ion. Difference between 10 to the minus 33rd and 23rd. Okay? So yeah, we would need 1,000,000 liters of this solution in order to guarantee we had at least 1 mercury ion free and available. This Kf is so enormous, it scavenges every single mercury ion. These bonds right here form so strongly that it takes every single mercury ion out of solution. Okay? Good luck, folks.